Hello, welcome back. I'm Dom, and this is the map of black holes, which isn't a map of where all the black holes are in space. It's a concept map of the subject of black holes, laying out our current knowledge of them, the evidence for their existence, and the many outstanding mysteries still to be solved. They're very strange and fascinating objects. I find concept maps are really useful to give you a good overall idea of a field of research. So here's the current state of knowledge about black holes.
On Earth, getting into space in a space rocket is really hard because we need to climb out of the Earth's gravity well. But in a way, we're lucky. If the Earth was just 50% larger by diameter, it would be impossible to get into orbit with any of our current technology. This would mean no astronauts, no satellites, no GPS or Google Earth. So the stronger the gravity of a planet, the higher the escape velocity you need. And black holes are the most extreme example of this, where the escape velocity exceeds the speed of light. There is so much mass squeezed into such a small volume that nothing can escape, because nothing can travel faster than the speed of light.
Hence the name black hole, which weirdly comes from the Black Hole of Calcutta, a notorious prison where people went in but nobody ever left alive. Although this name, black hole, only caught on in the late 1960s. Before that, they were referred to as dark stars, frozen stars, or gravitationally collapsed objects. The original idea that black holes could exist came from our understanding of Einstein's theory of relativity, published in 1915, where gravity is explained as the curvature of spacetime. The more dense an object is, the more it curves spacetime, and the more curvature there is, the stronger the force of gravity. In 1916, Schwarzschild found a solution to the field equations of relativity, which predicted a special distance from the black hole, called the Schwarzschild radius, but also known as the event horizon, and beyond which nothing can escape. This event horizon was long considered a mathematical curiosity until the 60s and 70s, where theoretical developments and experimental evidence mounted up, and people realized black holes did actually exist in our universe.
Here is a common visualization of the warping of spacetime around a black hole, although this is just a visual analogy. These squiggly lines represent photons, which are actually travelling in straight lines. They only look like they curve around because they're travelling through a curved spacetime. This phenomenon is known as gravitational lensing. The inner horizon is a feature of rotating black holes. Rotating and non-rotating black holes have got distinct features, which we'll see when we look at their structures in a bit.
At the centre of a black hole is the singularity, where all of the mass of the black hole is squeezed into an infinitely small region of infinite density, creating an infinite curvature of space-time. Well, that's probably not actually true. This is a strong indication that we're pushing the theory into a realm where it's not really built to cover. Really, we need a theory of quantum gravity, and people think that if we could add the laws of quantum mechanics to general relativity, this could explain what's going on in the center of a black hole. A theory of quantum gravity is the holy grail of theoretical physics, which is why black holes are so fascinating, because they're one of the few places in the universe where gravity gets big enough to be as strong as the other three fundamental forces. And so general relativity and quantum mechanics are both needed to explain what's going on inside black holes.
Another way to visualize the motion of particles near a black hole is using space-time diagrams. Far from a black hole, we see these squiggly lines traveling at 45 degrees, which represents light traveling at the speed of light. Because this is the cosmic speed limit, anything with mass will have trajectories at some angle in between these limiting cases, which is traditionally referred to as a light cone. As you get closer and closer to the black hole, this light cone bends towards it due to the curvature of spacetime. And if you cross the event horizon, all paths point inwards to the center,
which means that whatever direction you travel in, you're always moving towards the center of the black hole. Every possible future ends up with you getting squished. It's kind of like space and time switch roles, because outside the event horizon, time only goes forwards, but inside, the only direction you can move is forwards in towards the singularity. And it's called an event horizon because any event that happens inside the black hole can never be seen by anyone outside. So it literally is the horizon over which events can never be seen.
Most black holes that we know of are created from the remnants of dying stars. When stars exhaust their fuel, they perish in a variety of dramatic ways depending on their mass. Stars whose cores have a mass less than 1.4 times the mass of the Sun collapse into white dwarf stars. Above this limit, known as the Chandrasekhar limit, stars explode in a violent supernova and collapse into a neutron star. The incredible pressure of all that matter in the core overcomes the electrons' ability to repel each other, known as the electron degeneracy pressure, and the electrons and protons join together to make an incredibly dense star made of pure neutrons. Then above that, the theory says that a star with a core mass of above 2.17 times the mass of the Sun will collapse into an even denser object, a black hole. There is a possibility that there are other stars more dense than a neutron star and less dense than black holes, made of some form of exotic matter, perhaps quark stars or strange stars, but these are hypothetical and we've got no evidence of them so far. But exploding stars is only one mechanism for black hole formation. There are giant black holes out there called supermassive black holes with masses of millions of times to tens of billions of times the mass of the Sun. How they got so big is still an open question. Did they grow bigger over time, absorbing other matter in black holes? Did they form from the universe's earliest massive stars? Or perhaps they formed directly after the Big Bang from the primordial gas collapsing in on itself? We don't yet know, and this is still active research. At the small mass scale, it's theoretically possible to have very low mass black holes. The key feature of a black hole is not so much its mass, but the very high density of that mass. And so some people have wondered if tiny black holes might be created in particle collisions like in the Large Hadron Collider at CERN.
You might remember at the time a media scare that there might be black holes created in Switzerland that gobbled up the Earth. But this was total nonsense because we get particles from space called cosmic rays with way higher energies than anything we can create on Earth and anything that was created at CERN. And they don't create black holes in the atmosphere. So there's absolutely no evidence that miniature black holes are created from particle collisions. So perhaps there's a lower mass limit to black holes that we don't know about. But this is another open question.
Here's how the different masses of black holes are typically classified according to mass and size. Micro black holes would have a mass up to the mass of the Moon, but would be tiny, having a radius of their event horizons of 0.1 millimeters or less. Stellar black holes of approximately 10 times the mass of the Sun are about 30 kilometers in radius. Intermediate black holes are about 1,000 times the mass of the Sun, and are a similar size to the Earth with a radius of about 1,000 kilometers. Although the Earth actually has a radius of 6,000, so I kind of got this picture wrong. Supermassive black holes have masses from 100,000 times the mass of the Sun to tens of billions of solar masses, and they're so big they get as big as 400 astronomical units. For context, 1 astronomical unit is the distance from the Earth to the Sun, and so 400 astronomical units is about 10 times the orbit of Pluto. It's insane to imagine a black hole that big.
I just want to chime in here and say if you're enjoying this video, this black hole poster is available to buy at my DFTBA store. And also I'm very excited to announce that I've launched our Professor AstroCat books. They're written by me, illustrated by my friend Ben Newman. And if you enjoy my videos, this is basically the same kind of thing for kids. We've got books covering all of space, all of physics, all of the human body and all of the oceans. And each book comes with a free pack of postcards with some of my maps relevant to each book. We've been making these books for years and we've put a lot of love and care into them to make them as excellent as possible. So if you've got a youngster in your life who you want to introduce to science in a fun way, check those out too. Let's take a closer look at the anatomy of black holes. We've already talked about the event horizon and the singularity, but there are many other interesting features we need to talk about.
Near a black hole, clocks run slow. This is the effect of the highly curved spacetime which causes time dilation. This means that the experience of someone who's falling into a black hole would be quite different to the experience of someone watching them fall in. If you travelled over the event horizon, you wouldn't really notice anything. But then, depending on the size of the black hole, it wouldn't be long until you got completely spaghettified. If, however, you were watching someone falling into a black hole, as they approached the event horizon, they would steadily move in slow motion as their local clock slowed down. They'd also get more and more redshifted until they looked like a red smudge on the event horizon that gradually faded out of existence, as the wavelength of light they emit got longer and longer. And then we have the singularity, which I've already talked about, but basically it's a region of infinite curvature where all of the mass is squeezed into zero volume with infinite density. But this implies a breakdown of general relativity, and really a theory of quantum gravity is needed. So more important features of a black hole. Outside, at 3 times the Schwarzschild radius, is the innermost stable circular orbit, which is the minimum distance a test particle could orbit the black hole in a circle, and this marks the inner edge of an accretion disk of infalling matter around the black hole. And at 1.5 the Schwarzschild radius is the photon sphere, which is the only possible circular orbit for a massless particle. And if you sat here, because photons are going all the way around the black hole, you could look at the back of your own head. This also marks the closest distance any elliptical orbit of any kind of matter can get. If anything travels below this, it'll either get slingshotted out of the black hole's gravity, or eventually spiral in. Also, black holes give off Hawking radiation from the event horizon, although this is very, very faint, and it's impossible for us to detect this unless we could somehow get very, very close to a black hole.
It's worth noting here that black holes don't have any special suction powers where they go around the galaxy hoovering everything up. The gravity of a black hole is the same shape as any other massive body. So at a distance, being around a black hole would feel just like being around any other star with the same mass, gravitationally speaking. They're special because they're so dense, so when you get close into them, you experience a way higher gravity than you could ever get anywhere else.
This picture so far only applies to non-rotating black holes. The picture for a rotating black hole is a little more complicated as shown here.
Now you may wonder if you ever get non-rotating black holes, as everything in the universe that we see is spinning in some way. But theoretically, you can get non-rotating black holes because Hawking radiation takes away some of the angular momentum from the black hole, which would gradually slow down their spin. But it would take a very, very long time for this to happen.
Non-rotating black holes are spherical, but rotating black holes are a squashed oval shape. Also, the singularity in the center is no longer a point, but a singularity ring. And they have a region outside the event horizon called the ergosphere, which is a region where it would be impossible to stand still because the rotation of the black hole drags space-time around it in a process called frame dragging, which is kind of like a whirlpool of space-time. And the frame dragging is so fast inside the ergosphere that you'd have to travel faster than the speed of light just to stand still. So you can move around in the ergosphere, but only in the direction of the rotation of the black hole. At the edge of the ergosphere is the innermost stable orbit, the minimum distance to the black hole a particle can maintain a stable orbit. Many real black holes are surrounded by an accretion disk, a cloud of material that's falling into the black hole and generating lots of heat and energy as the particles speed up and crash into each other. Accretion disks are very bright sources of X-ray radiation and high-energy particles which can fly out of the ergosphere with way more energy than they entered, stealing angular momentum from the black hole as they do so and using it as a slingshot. Finally, the incredible gravity around a black hole leads to some interesting gravitational lensing effects on the accretion disk, resulting in this familiar image. In reality, the accretion disk is actually a pancake shape, but we can see the accretion disk that would normally be hidden behind the black hole because the light from it, which travels upwards or downwards, is bent around the black hole and comes towards us. So it looks like there's an accretion disk above and below the black hole, but we're actually seeing the top and bottom of the accretion disk that's behind the black hole.
I've been talking for a long time about the theory, but how do we know that black holes actually exist? Well, over the last 50 years, we've built up a large body of observational evidence from many different techniques.
The first was from X-ray astronomy, as the radiation from the accretion disk is mostly X-ray radiation. The process that produces this X-ray radiation in the accretion disk is one of the most efficient energy-producing processes known, where the spiraling material gets up to 40% of its rest mass converted into energy. To understand how hugely remarkable this is, we can compare this to the nuclear fusion process that powers the sun and all the stars. Here, only 0.7% of the rest mass is converted into energy, way less than 40%. So the accretion disk is nearly 60 times more violent than a burning star. The very first black hole that was discovered this way in 1971 and is called Cygnus X1. Since then, we've discovered around 100 more, although this is just a tiny sample of the number of black holes that are thought to exist in our galaxy, and every single galaxy is thought to have a supermassive black hole in its center. Often, accretion disks are accompanied by relativistic jets which emit even higher energy particles and radiation than from the accretion disk. The mechanism that creates these jets is not currently known. We see many high-energy sources in space, and we think many of them are caused by the accretion of matter into black holes. These include active galactic nuclei and quasars, which are thought to be the accretion disks of supermassive black holes, and also ultra-luminous X-ray sources thought to be from intermediate-mass black holes. Also, things called X-ray binaries are most likely to consist of a normal star and a black hole orbiting each other, while the black hole gradually sucks away matter from the star. And short-lived streamers are thought to be stars which shine incredibly brightly as they're being swallowed up by a black hole before disappearing. An entirely different line of evidence comes from the center of our own galaxy by tracking the orbits of about 100 stars, which have been observed to be orbiting around an invisible massive object called Sagittarius A star. By tracing the orbit and measuring the velocities of the orbiting stars, astrophysicists have been able to calculate the mass of the central body to be a humongous 4.3 million times the mass of the Sun. But this mass is confined to a region of less than 0.002 light-years, signs that it must be a supermassive black hole. Even more recently, in 2019, the first direct image of the accretion disk around a black hole was constructed from the radio waves emitted by the galactic center of the Messier 87 galaxy, and it had the features of an accretion disk that we expected, if a little blurry. But constructing this image was a feat of radio astronomy and was achieved by combining the signals from 8 radio telescopes all around the world to create a virtual telescope the size of the Earth, an amazing achievement. Just as incredible was the detection of gravitational waves by LIGO in 2016, which uses finely tuned lasers in a giant L shape to detect the minuscule changes of distance caused by the rippling of space-time when gravitational waves pass through the Earth. The first gravitational waves they detected were created by a pair of stellar mass black holes spiraling into each other and finally merging into a larger black hole and converting around 5% of their mass into gravitational waves. And since then, LIGO and Virgo have detected many more collisions. Finally, there's a proposed method called microlensing, which has been seen many times for stars, but not as far as we know for black holes. I've talked about how the strong gravitational field around a black hole causes a lensing effect. The idea is we could use this to detect black holes when they pass in front of a star. We've seen things like supernovae be gravitationally lensed by massive objects like entire galaxies, but if we found a binary system where a star is orbiting a black hole, we could potentially see the radiation from the star being bent towards us as it passes behind the black hole, which would give us information about the black hole it's orbiting, and would be a really cool technique for the future of black hole observations.
Now let's take a quick look at the theoretical understanding of black holes, which started in 1916 but was really fleshed out in the 60s and 70s when black holes were taken seriously as real physical objects, not just mathematical curiosities.
Here is the equation for the radius of a non-rotating black hole, which gives a simple relationship with its mass where g is the gravitational constant and c is the speed of light, but this gets more complicated if the black hole has spin or charge. The general description of black holes, developed in the 60s, is called the no-hair theorem and states that a stationary black hole can be completely described by just three parameters: mass, angular momentum, and electric charge. Then, in the 70s, a theory of black hole thermodynamics was developed which describes the links between black hole mass and energy, how the surface area of a black hole relates to its entropy, and how the surface gravity relates to temperature. Then Stephen Hawking applied quantum field theory to black holes and showed that black holes radiate Hawking radiation, energy from the event horizon, with a characteristic black body spectrum where the temperature is proportional to the surface gravity of the black hole.
So black holes will gradually lose their mass over time by radiating away Hawking radiation. But this evaporation is slowest for the largest black holes and fastest for the smallest black holes, which means that micro black holes would be very short-lived, but supermassive black holes will live for over 10 to the 100 years, which is a ludicrous amount of time. And those will be the last objects that will exist before the heat death of the universe. What is going on? Oh, it's just a car. This all gives you a good idea about what we think we understand about black holes, but there are many outstanding mysteries which we know about. And these all seem to boil down to our lack of a theory of quantum gravity. I've already mentioned how singularities probably don't exist, because you can't have a thing that's infinitely small with infinite density. So there's a question, what actually happens to matter at the singularity? Unfortunately, if we ever found out experimentally, because of the event horizon, we couldn't ever get the results out to anyone, which is a bit of an issue to ever figure out what's going on in the singularity.
Also, in the description of spinning or charged black holes, there's a hypothetical possibility of them containing an unstable wormhole, which would let you leave the black hole but in a completely different spacetime. They also have regions inside them where it would be possible to travel to your own past along closed time-like curves, which creates one of those time travel grandfather paradoxes. But although these ideas are tantalizing from a science fiction perspective, both of these will probably go away with a proper quantum description of black holes. There are other theoretical objects which have been conjectured, but there's no evidence for them yet. These include stars somewhere in between neutron stars and black holes, but these are all highly speculative. Also, white holes, which are like black holes, but where the event horizon goes the other way, information can come out, but nothing can ever go in. And finally, naked singularities, which are singularities which could be observed because they don't have an event horizon. But these are thought to be unphysical and so not actually possible. But these aren't as interesting as the real theoretical puzzles. First of all is the holographic principle, which is complicated to explain, but the general gist of it is that black holes might be telling us the whole universe is actually a hologram. This is a strange result of the entropy of a black hole. In every other thing in the universe, entropy scales with the volume of that thing, but in black holes it scales with the surface area. And this implies that anything that happens within a volume of space-time can be described by data on the surface of that volume. So, we're all a hologram. But again, we'd need a theory of quantum gravity to properly calculate the entropy of a black hole, so this is still active work.
Finally, we have one of the biggest unsolved mysteries of black holes. What happens to the information that falls into them? Now, because black holes are only defined by three parameters, mass, charge, and angular momentum, any other information about objects that fall into the black hole appears to be erased from the universe. But the thing is, this isn't actually allowed by a fundamental law of quantum mechanics called unitarity. So, for example, an electron has got a load of quantum numbers associated with it that define it, like lepton number. But if an electron falls into a black hole, this information's lost because the black hole only preserves mass, charge, and angular momentum. So one attempt to explain this is a theory called complementarity, which says that the information does actually come back out again, but in the Hawking radiation. Trouble was, this was shown to fail by a further paradox called the firewall paradox, Now, the details of all of these things are quite complicated, but the end result is that to resolve all of these paradoxes about information, we may need to give up one of the fundamental rules in the laws of physics. Either Einstein's equivalence principle, unitarity in quantum mechanics, or local quantum field theory. But overall, I hope I've conveyed why black holes are such fascinating objects to study, as they're the most extreme environments in the universe where gravity and quantum physics meet. And their very existence seems to break our fundamental theories of physics. But by studying them, the hope is we may actually uncover some subtle clues that could help guide us to the next level of understanding. So perhaps black holes are actually the experimental key to developing a theory of quantum gravity. Or perhaps we'll just be as confused as we are now forever.
This section of the video is sponsored by Brilliant, a long-time supporter of this channel, and because of that you may already know that it's a website and app based on the idea that active problem solving, rather than just watching videos, is the best way to properly learn a subject by actually sitting down and solving problems, and I agree. Brilliant have recently increased the interactivity on their platform to a new level with new tools so that you can get in and get a feel for what you're learning, like this lesson on the centre of mass where you can shift around the balance points to see how these weights balance or don't. And if you want to learn more about gravity, they've got a whole course on gravitational physics where you can gain a mastery of concepts like escape velocity, orbits, or gravitational fields. If you're interested, go to my special link, brilliant.org/DOS. You can click on the first link in the description below. And this helps me out because they know you've come from here. And on top of that, the first 200 people to sign up via the link will get a 20% discount on the premium subscription, which unlocks all of their content. A big thanks to Brilliant for all of their support on this channel, and a big thanks to you for watching. I hope you've enjoyed this video, and I'll see you on the next one.